In this video, we will look at the various oxidation states exhibited by the D block elements and see how they differ from that of the non-transition elements like, let's say, those of the P block. The D block elements exhibit a variety of oxidation states. In other words, variable oxidation states, as you can see from this table here. The highlighted ones or the ones in the cyan color are the most common oxidation states. As you can see here, there are only two elements that show a single oxidation state, and those are found at either extreme ends of the series, which are scandium and zinc. Scandium shows only +3 oxidation state, whereas zinc shows only +2 oxidation state. Both of these are favorable oxidation states as they result in a stable electronic configuration. In +3 state, scandium acquires the noble gas configuration, whereas in +2 state, zinc acquires a stable D10 electronic configuration, which as we know is again a stable state. Another thing that we can observe from here is that fewer oxidation states are observed in elements which either have too few electrons to share or lose, like in the case of scandium, or the element has too many d electrons, as we can see in the case of zinc. Now, when we have too few electrons to share or lose, obviously that limits the number of oxidation state. That is why scandium does not really show a variable oxidation state. On the other hand, the consequence of too many d electrons, like in the case of zinc, is that you don't have enough orbitals available to share these d electrons with other elements. So once again, that results in limited number of oxidation state. But if you compare these elements with those elements that lie towards the center or the middle of the series, you can see that the ones at the middle exhibit maximum number of oxidation states. Look at manganese, for instance. Manganese shows oxidation states corresponding to the loss of electrons present in both 4s and 3d orbitals. That is, it ranges all the way from +2 to +7. +2 when it loses 2 of the 4s electrons, and +7 when it loses all of the 3d as well as 4s electrons. Now here again, as you can see, +2 and +7 are the most stable oxidation states for manganese because both of these states result in stable electronic configurations. In +2 state, you get half-L D5 electronic configuration, and in +7 state, you get noble gas configuration. Now, both of these states are most preferred because they result in stable states. Now, as we observe the oxidation states from scandium to manganese, another thing that we can see is that the maximum oxidation state corresponds to the sum of the electrons present in 3d and 4s orbitals. Like in the case of titanium, the outer electronic configuration is 3d2, 4s2, right? And that is why the maximum oxidation state corresponds to the sum of the 4s and 3d electrons. Similarly, in the case of vanadium, chromium and manganese, the highest oxidation state corresponds to the sum of the electrons present in both of these orbitals. However, from iron to zinc, if you see, we can notice a decrease in the stability of the higher oxidation state. In iron, the most stable state is +2 and not +6. Similarly, in cobalt and nickel, the most stable state is again +2 and not the maximum or highest oxidation state, which is +4. Now, this decreasing stability of the higher oxidation states is because of the unavailability of empty d orbitals, or in other words, presence of too many d electrons. This is why lower oxidation states get favored in elements ranging from iron to zinc. Now, these variable oxidation states are an important characteristic property of the D block elements. And as we saw, this occurs due to the incomplete filling of the d orbitals. Now, another interesting feature that might catch your attention is that the oxidation states in each of these elements differ by 1 unit. +2, +3 and +4 in titanium. In copper, +1 and +2. Now, this is quite different from non-transition elements where the oxidation states usually differ by 2 units. For example, the common oxidation states of group 15 are -3, +3 and +5. Similarly, in group 16, the common oxidation states are +6, +4, +2 and -2. As you can see in non-transition elements, like if you look at the p block elements, the oxidation states of elements usually differ by 2 units, whereas in that of d block elements or the transition elements, the oxidation states differ only by 1 unit. Now, this is not the only difference between transition and non-transition elements. A contrasting feature between d block elements and p block elements is the stability of the higher oxidation states. Now, do you recall that in the p block elements, the lower oxidation state or the stability of the lower oxidation state increases as we go down the group? Yes, it was due to a phenomenon called inert pair effect. So because of that, if you look at group 15, the lowest or the heaviest member like bismuth was more stable in +3 oxidation state and not in +5 oxidation state, which was the group oxidation state, right? So here the lower oxidation states were more stable or more preferred. However, in d block elements, it was found that as we go down the series, higher oxidation states become more stable. For instance, molybdenum 6 was found to be more stable than chromium 6. Similarly, tungsten 6 was found to be more stable than chromium 6. That is, higher oxidation state was found to be more stable as we go down the group. A highly simplistic explanation for this could be that the 3D orbitals, or if you look at the 3D series, chromium is a 3D series element, right? So the 3D orbitals are smaller and more compact and also closer to the nucleus than 4D and 5D. So this means that 3D electrons experience greater nuclear attraction as compared to the ones in 4D and 5D orbitals. So because of this, what happens is the 3D electrons are held closer towards the nucleus and they become less participative in chemical reactions. Whereas the 4D and 5D electrons are more free to participate in chemical bonding, and this makes the higher oxidation states more stable in the heavier elements.